Okay, so welcome back. Today we are going to talk about how you can do some very simple code to simulate objects like you see here. And I'm shooting some objects out of a cannon. And you can see they're flying across and they're under the influence of gravity. And it turns out this is very simple to simulate. And we're going to show you how with just a couple equations in your code you can do these two-dimensional simulations. Now, I know in this world it's all about, when you talk software, it's all about playing video games and picking up a gun and firing and blowing people's brains out. So I know a lot of people are interested in that. Personally, my interest is because over many years I've seen even professional animators do objects like this, and they either intentionally or unintentionally ignore how they should respond in the real world. And you get animations that subconsciously look bad. They don't look real. So here we're going to show you how to implement those fairly quickly. And again, it doesn't matter what language you're using. We're going to use C++, Visual Studio, but these simple equations work in any language. So let's start out here in Blender, and I'll show you why this is so very important if you're going to do some decent 3D animations. So here I've got a simple scene in Blender, and I've got a monkey head here and a ground, and we want to simulate that falling from some height. Now, a lot of people, what they'll do is say, well, I've got it here, and I will keyframe it here, and I don't know, it takes maybe a couple seconds to fall to the ground. So then I'll bring it down to the ground and keyframe it, and you'll get something like this, right? Now, subconsciously, you might realize that something doesn't look right there, right? Because it seems very stiff and not realistic. There's not a lot of impact there, right? It just goes from one point to the other. Let's now take a look at an actual physically simulated in Blender monkey head right next to it on the left, and here's how it would actually fall. You see it starts out slow and then it speeds up and then it bounces. So this looks like a head that was, a large head that was falling a great distance, and this looks very lightweight and it's not realistic, okay? So that kind of stuff happens all the time when you see animations. People don't understand how to do the simple, even the simple falling under gravity is a very simple equation that you can use, but people don't want to get involved in that. They just say, close enough, and they think it looks real, and it really looks bad. Now, what you can do is you can, using some equations, you can come up with a few keyframes using the correct values. You can come up with this monkey on the right that matches pretty much this one that is actually physically simulated. All right, so it doesn't take a lot. It's just solving a simple equation and you're good to go. So really important that you do this keeping in mind the actual physical real world if you want your viewers to be impacted by it. So now let's first take a look at gravity and see how incredibly simple it is to simulate something falling to the ground under the influence of gravity. So here's a simple example. Let's say I'm up at a platform and I've got a box, and I want to push the box over the ledge and simulate how it falls to the ground. So what we need to know is for every point in time as this thing falls, what distance has it fallen? So we need some sort of equation to say if I push it off, after 1 second it's fallen this far, and after 2 seconds it's fallen this far, and so on. Because let's say I want to do an animation, I want to keyframe the different points for my object falling versus time. So I need to have an equation of the distance versus time. So how do I do that? Well, if you look up here, this is the extremely simple equation that defines the distance an object has fallen for every point in time after you drop it. And it's 0.5 times g, which is basically a constant value that defines how much the Earth's gravity is pulling on the object, and t is the time. So after 1 second, you put 1 in here. After 2 seconds, you put 2, and so on, and just solve this equation. Now the G is a constant value. It doesn't change. It's a very simple number. So you just have to plug in this number into G. In the imperial system here in the US, that is 32 feet per second every second. It defines how fast the object will accelerate towards the ground every second. So to solve for the distance it has fallen, just 0.5 times 32 times whatever the time is you're calculating the distance. So the distance an object has fallen in feet is 0.5 times 32 times time squared. So you just fill in the time. And that will define this distance it has fallen due to gravity. Now if you multiply 0.5 times 32, it's even simpler, it's 16. So you just figure out what time you're solving for. So say if it's 1 second, the distance it has fallen is 16 feet. If it's 2 seconds, 2 squared is 2 times 2 or 4 times 16 is 64. So very simple equation. You just put in the time and it gives you the distance it has fallen. Now, one thing is very interesting to notice. Here is our equation, distance equals 16 times time squared. Nowhere in this equation does it say anything about the object itself. It doesn't say in here that, it depends on the weight of the object. No, it is independent of the weight of the object or any other object parameter. All objects fall at the same rate, no matter how heavy they are. Now that may make your brain explode, but that's true. Every object falls at the same acceleration due to gravity. Now, there is a caveat in there. If you have like air friction pushing against the object and keeping it from falling only due to gravity, it might slow it down a bit. But without any other factors like that, just due to gravity, something will fall with this equation. And we're going to assume that this is what we use to solve for the falling object. We're going to ignore friction due to air and anything else. So again, very, very simple equation that you can use to, if you're going to do animation of a 3D object, you can enter this value. You can solve it for each time step. Enter this value, and then you can keyframe your object in your animation. For some reason, people are afraid of this. They don't want to do that, but it's very, very, very simple. As an example, 16 times time squared. If you're doing an animation at 30 frames every second, then after 30 frames of your animation, that will be 1 second. So at 1 second, you put in 1 times 1 times 16 is 16 feet. So after 30 frames, it will have fallen 16 feet. Independent of the object, independent of its weight, it will have fallen 16 feet. After 60 frames, or 2 seconds, put in 2 to time. 2 times 2 is 4, times 16 is 64 feet. So after 1 second, it's fallen 16 feet. After 2 seconds, it's fallen 64 feet. What do you notice here? Well, it falls 16 feet in the first second, but in the next second, it falls a lot more. It's now down at 64 feet, which means it is speeding up. It is accelerating. It's like putting your foot on the gas pedal. It's going faster. After 3 seconds or 90 frames, 3 times 3 is 9, times 16 is 140 feet. It's accelerating even more. So you can see when you drop it, it starts out going very slowly, but as time goes on, it accelerates towards the ground. So it's going faster and faster. And that's one thing that people tend to not understand and avoid when they're doing animations. They think everything falls at the same speed. That's just not true. And your mind subconsciously says, hey, wait a minute. If it's falling at the same speed, that's not right. It's supposed to start off slowly and accelerate towards the ground. Now, the next thing we're going to talk about is projectile motion. So let's say I've got an object I'm going to shoot from a cannon starting at the initial 0 point, and I'm going to fire it at an angle, whatever angle I choose, and it's going to have an initial velocity. When it comes out of the cannon, it's going to have a speed. and the cannon accelerates it from 0 to whatever that speed is. But after it's out of the barrel of the cannon, it's now going under the influence of gravity and this initial velocity. So it's going to be a projectile that also is under the influence of gravity. So we've got our gravity equation, and we're going to have to add that to another equation to figure out the xy coordinates of that object over time. So we've got a starting angle and an initial velocity. With those two numbers, we can calculate the xy position of the projectile over time. So these two equations right here define projectile motion. These are the only two equations you need to define those projectiles we had in the original simulation. There is an x location and there's a y location. The y location is the up and down, and that is affected by gravity. You might notice over here we've got this factor, which is 0.5 times g times t squared. That is what we just discussed previously about the influence of gravity on our projectile. So the y, or up and down position, is dependent on the gravity factor. So the gravity is pulling this thing down, which is affecting the y location. The x location, it's not affecting it. The x location only depends on the initial velocity. So, for example, my x location is the initial x location, or x0, which is this point down here, which is 0, 0, plus the initial velocity, which is the velocity coming out of the cannon, the speed coming out of the cannon, times the cosine of whatever angle we fired it at, times the time. At time 0, it's at the initial position. And as you add time to it, you're going to get a bigger factor here. Now, if the initial velocity is 0, then the x location isn't going to change, because 0 times this is going to be 0, and all you've got is the x0 location. So if there's no initial velocity, it's not going to move. If you want to calculate the x location of the object over time, you use this simple equation. The initial position in the x-coordinate plus the initial velocity times the cosine of the firing angle times the time. So you just fill in the time, you know what the angle is, you know what the initial velocity and initial position are, and that gives you the x location at every point in time. The y location is almost identical. y0 plus v0 times sine, not cosine of the angle, times time, and you are adding this gravity factor. So, very simple way to calculate the x location and the y location at each point in time based on these known values. So, very simple to calculate those projectile positions, x and y locations, at every point in time. Just solve these equations. So now let's think about how we're going to put this into our simulation. So we saw before we've got 1, 2, 3, 4, 5 projectiles coming out of this cannon. And we know it's going to be a time simulation in seconds, because we have to solve these equations every 1/10 of a second or whatever. So we're going to have some time simulation, which means there's going to be a program loop. And I'm going to assume you know how to do a simple while loop or a program loop, that every whatever time step you have is going to go through and solve your positions. So for each object, we see there's 1, 2, 3, 4, 5 objects, and each object has a different position. And this is for one point. This is a snapshot of one point in time in our simulation. So we're going to need for each object the XY positions at each time step. So I need a XY position for this guy, for this guy, for this guy. So you can start to think, maybe I need to have maybe a vector of the X positions of each of these objects and another vector of the Y positions of each object at each point in time. So all of these X positions, and then the next time step, I'll overwrite those and put in new ones. And we know that each object that we saw in the simulation has its own firing angle. You don't need to do that, but I just added a different firing angle for each object. So maybe we might have another vector of firing angles for each object. And then simulation times. This object is operating on a different time since it was fired than this guy, right? This guy hasn't been fired yet. This guy was fired maybe 5 seconds ago. So each object is going to be working on its own individual simulation time, right? They're going to be different simulation times. So again, we might be needing a vector for each object of its own simulation time, right? So if you look at this, we're going to need some vectors of positions and simulation times and maybe even firing angles. Also, each object, there was a delay between the time I fired this guy and this guy and this guy. So we're going to need a delay that defines how often I fire the projectile. So now we've got an idea of what we're going to need. We're going to need a program loop, and we're going to need some vectors for each object, defining the positions and the firing angle and the simulation time. So how are we going to implement that? Assuming we've got this general information, what we're going to want to do is we're going to want to calculate each object's XY position at each time step, right? We go through our program loop and we calculate the XY position. Then what we're going to have to do is keep in mind these values are XY positions in feet in the real world, right? These equations are in feet in the real world. They don't tell you where to place it on this window, what pixel position. So we've calculated all of these XY positions in the real world, but we need to somehow map those real world XY feet distances to pixels. So we're going to have to figure out, once we've calculated the positions, how do we map that to the visible window? So once we figure that out, we're going to draw the black background and then step through each object and draw it over the background, and then increment each object's time step, and then do it again and again and again, okay? So this is kind of the program flow we're going to need to develop to do this. Okay, so here we are back in our application. Again, this is Visual Studio C++. Again, it doesn't make any difference what language you use. In this case, I have a framework that is using IMGUI for this graphical user interface. Again, it doesn't matter. I'm not going to go through how to set all this up. If you've ever worked in C++ and tried to put a framework together, you know it takes weeks to get all the different components together and working. So we're just going to focus on the code we need to do these simulations. And then I'm going to assume you'll be able to do a program loop and print these projectiles on the screen. So what you see here on the screen is basically all the code, mostly all of the code I need to do what we talked about before. And at the top here, we've got our button that says fire. If that button was pressed, then it goes through and does what we talked about before. It calculates the XY positions for each object in the present time step. So what I've done is I've set up vectors describing, in this case, the X location of each of the 5 objects and the Y location of each of the 5 objects at this time step. Now, this code is going to be executed every time step for this application. In my case, this is running at about 60 frames per second, so every 0.0167 seconds, it's going to calculate this code. I'm looping for int I 0 to less than 5, which means it's going to go through for each of the 5 objects and figure out the X location. And we're just using the equation we showed before. X location initial plus initial velocity in feet per second times the cosine of the firing angle, and here I've got a vector for each of the objects, what the firing angle is. So that's why it's shooting it out at different angles, each projectile at different angles. And then I am taking that angle in degrees and converting it to radians so I can do a cosine. So firing angle in degrees times pi over 180 gives me radians, and I just do a cosine, times the sim time for that object. So sim time I gives the simulation time for that object. Y location for that object is very similar as we said before. Y location initial plus initial velocity feet per second times sine, or the y coordinate of the initial velocity, times firing angle degrees for that object, times pi over 180 times the sim time of that object, and we have to include the gravity effect, 0.5 times 32 times simulation time squared. So this right there is all the equations we need to calculate the x and y location at each point in time for each object. Very, very, very simple. Now, what we talked about before is there's two more things we need to do. One is we need to map those real-world feet, x and y locations in feet, to pixel values so we know where to place it in the window. We're not going to go through that in this video. We'll talk about that later. It's very simple to do. Then what we want to do is do a clamp for each of those locations that we have mapped. We also don't want it to go outside the visible window like we showed here. So we fire the projectile. We don't want it to go past this wall. So it hits the wall, and each one of these, as they hit the wall, they stop and then they just drop. And also with this X position, we don't want it to go below that. So that's why we have this clamp screen to make sure that the projectiles don't go out the window. And once we have taken the X location in feet, mapped it to pixels, and replaced the X location with the pixel value, then we've clamped it to the screen and replaced the X location now with a clamped value, we can actually draw the box at each location. And we won't go through how to draw the box. We'll talk about that later, but that's basically all we need to get the information so we know where to draw each box, and there's 5 boxes, where to draw each box in the window. Now, once that's done, we have to generate and update the individual simulation times for each of the 5 projectiles. So again, we're going to go through a loop from 0 to 5. If the sim time main, I've set a main simulation time for the entire simulation. If that is greater than I times the firing interval in seconds, we need to take the main sim time, and if that's greater for each object, then the object number times the firing interval. That will allow us to increment for each object simulation time, increment, in this case 0.01667, since I'm going at 60 frames per second. 1 frame, this is going to go through at 0.01667, something like that. So I'm just incrementing each individual simulation time. And then at the end, I'm incrementing the main simulation time. So then when we go through again, it will increment each individual. So that's about it. Really, 2 equations, you need to map them, you need to clamp them, and then you can draw them. And you just need to make sure that you are updating the individual simulation times. So anyway, I hope that helps. In subsequent videos, we'll maybe look in more depth at these, how do you do the map ranges, and maybe more about the simulation time stuff. But that's the basic core of how you can do a projectile and gravity simulation in your software. Anyway, if you like any of these videos, I encourage you to hit the like button, subscribe, hit the bell notification, and please, most of all, let others know that we're here so we get some views. Otherwise, take care. Have a really good day. Thanks.